To the untrained eye, powder X-ray diffraction data looks straightforward. You get a baseline, a handful of sharp peaks, and a list of intensity values. But materials scientists demand a lot from this seemingly simple readout. We use these patterns to identify exactly which crystalline phases are present, determine their precise weight fractions, and calculate whether microstrain is actively building up inside a crystal lattice. Moving from that initial graph to an actual defensible structural model does not happen by just pushing a button. Real samples are messy. They generate overlapping peaks. Background fluorescence clouds the baseline, and the diffractometer itself introduces geometric artifacts that physically distort the true signal. Extracting real material properties requires an active, mathematically rigorous modeling strategy designed to explicitly separate the geometry of the instrument from the chemistry of the sample. That separation is the primary function of Profex 5.7.1, an open-source analytical environment built specifically for this kind of high-level diffraction analysis. At the core of the software is the BGMN kernel, a mathematical engine dedicated to Rietveld refinement. Instead of looking at individual peaks in isolation, Rietveld refinement treats the entire pattern as a single system. It takes a calculated, theoretical diffraction pattern based on known crystal models, and iteratively adjusts its parameters until it matches your physical measurement. Profex does not attempt to automate scientific judgment. Its entire interface is designed to enforce strict, systematic physical constraints on the data you are fitting. It exists to give researchers a fully auditable trail. You start with a raw, noisy scan, and through applied physics, arrive at a chemically sound conclusion. In a working lab, you rarely analyze a single scan. You compare dozens of them. When you overlay those patterns, you frequently see slight shifts in peak position along the x-axis. The danger lies in interpreting that movement. You must separate mechanical error from a shifting lattice, splitting data into two paths. One is true physical phenomena, like thermal expansion genuinely moving peaks. The other is artifacts, where hardware misalignment produces the exact same visual movement. Profex addresses this ambiguity directly with the EPS2 scan displacement toggle. This specific interface feature allows an analyst to instantly set, reset, or completely disable scan displacement directly from the plotted view. It forces a hard boundary between visual alignment, used for a quick inspection of the data, and the mathematical modeling of a true structural shift. By isolating scan displacement, you prevent spending hours mathematically modeling a structural anomaly, only to realize the sample holder was simply crooked. Before you can ask the algorithm to evaluate a crystal structure, you have to define the exact geometry of the machine taking the measurement. Every diffractometer inherently distorts the incoming signal. A mathematically perfect, sharp reflection emerges on the screen as a broadened, asymmetrical curve. Without an accurate instrument geometry model, the math breaks down, forcing sample parameters to artificially absorb the difference in crystallite size or microstrain. The primary defense against this error is the BGMN-based instrument configurator built into Profex. The 5.7.1 update refines this further by introducing a new detector model option, allowing for an even more precise geometric description of modern lab hardware. Establishing this realistic baseline restricts the algorithm. It removes the mathematical temptation for the software to invent false microstructural parameters to explain a simple hardware footprint. An accurate instrument model acts as a structural firewall. It guarantees the physical insights you publish belong to the material, not your detector. Modern diffraction analysis increasingly relies on high-volume, continuous data, tracking a sample through temperature ramps, or capturing a battery actively cycling operando. Not every experiment requires a complete crystallographic map. Tracking a single peak's position and width is often enough to monitor a phase transition.
The standard approach to this time series data is fitting each sequential scan independently, but treating each time step as an isolated universe introduces random mathematical noise, obscuring the actual physical trend. Profex 5.7.1 tackles this dataset problem by allowing the linear modulation of coupled variables. A coupled variable mathematically anchors a specific peak parameter, like its width or position, across sequential scans. Linear modulation forces that tethered parameter to vary systematically along a defined trajectory. The parameter can shift, but cannot jump randomly from scan to scan. You can track continuous material degradation or subtle phase evolution without letting the math drift off course. By locking variables into a continuous trend, labs capture the true physical evolution of a sample, actively preventing the overfitting of isolated noisy data points. The reality of RETVAL refinement is heavily iterative. A single project rapidly spawns dozens of test folders, intermediate parameters, and discarded runs. When analytical software makes this iteration difficult to organize, researchers lose track of what parameters produced which outputs, entirely destroying the reproducibility of the analysis. Profex addresses this lab disorganization directly with a refined project selection dialog featuring built-in status indicators. These visual filters allow a researcher to instantly locate a stable, completed refinement and quarantine failed or unfinished tests, maintaining a clean chain of evidence. The software also removes friction from the visual analysis itself, most notably by allowing instant offset application in the plot options for stacked datasets. Previously, adjusting a visual offset required a tedious cycle of clicking, waiting, and rechecking. That delay is now gone. While instantaneous plotting sounds like a minor quality of life update, it directly influences researcher behavior. When the data moves the moment you interact with it, you inspect the scans much more frequently. Stripping away interface friction forces deeper engagement with the raw data, and continuous visual inspection is exactly how you catch a fragile, overfitted model before it becomes a published conclusion. The ultimate trap for any diffraction analyst is looking only at the numbers. It is incredibly easy to rely entirely on the residual error statistic as absolute proof of a successful refinement. Standard evaluation requires meticulously reviewing the difference curve, the visual gap detailing exactly where the mathematical model misses the measured data. A mathematically flawless fit, complete with a perfectly flat residual line, can easily be faked. Analysts achieve this by phase shopping, adding unverified chemical phases or unjustified parameters just to force the math to match.
If you alter the instrument model or drop in a phantom material simply to flatten that curve, you completely break the chemical and physical plausibility of the actual sample. A low residual is merely a single input. If the refined parameter values do not make absolute physical sense, the math might be perfect, but the refinement has failed. Analytical software is an instrument. It structures the data and executes the calculations, but it can never replace human scientific judgment. That is precisely why the open-source architecture of tools like Profex is critical for the future of materials research. It removes financial barriers for smaller labs while providing total, uncompromised transparency into exactly how every mathematical parameter is handled behind the scenes. As multi-scan experiments scale up in complexity, the workflows used to analyze them must be entirely traceable. Results need to be seamlessly exported to standard formats, maintaining an auditable chain of custody from the initial scan to the final structural file. The next generation of materials research will certainly be built on faster detectors and larger datasets, but its scientific validity will rely entirely on our ability to turn that complex diffraction data into a transparent, shareable, and strictly defensible physical truth.